So this session is about something called impulse, and it's the connection between force and momentum, and it is often related to objects hitting other objects, such as a golf club hitting a golf ball or a foot kicking a ball. Let me explain how this comes about. I've got to kind of do a F equals ma makeover. So I'm going to look at this, but look at it from a different viewpoint. So I'm going to think about F equals ma, but acceleration I'm going to expand out to the final velocity minus the initial velocity divided by t. Okay, so getting back to basics. If I do that, then I can rewrite F equals ma as F equals m multiplied by v minus u divided by t. If I multiply that out, it becomes F equals mv minus mu divided by t. Now straight away we're going to recognize that's interesting, because what we have now is the final momentum minus the initial momentum divided by the time taken for that change to take place, which is really force is equal to the rate of change of momentum. Okay, so we're bringing force and momentum together. Force is equal to the rate of change of momentum. We can then restate Newton's second law as resultant force is equal to the rate of change of momentum. So this forms the basis of Newton's equation F equals ma, but it can be shown as F equals mv minus mu divided by t. So exactly the same Newton's second law idea, but just interpreted in a new way. Can also be shown as force is the change in momentum divided by the change in time. Okay, so we can see here, for those who like a little bit of calculus kicking in, and we're going to use that in a few moments time, although for the IB we're not actually going to use any differentiating, but some of the ideas about the area underneath a curve. So there's this thing called impulse. Now if I rearrange F equals mv minus mu divided by t to give Ft equals mv minus mu, I have an interesting statement. Ft, force multiplied by the time it takes, is known as the impulse. The impulse of the force is equal to the change in momentum. So the impulse of a force is the force multiplied by the time taken. Okay, so that means the units are going to be Newton seconds, and it's equal to change in momentum. Please make this clear that impulse is not the rate of change of momentum. Okay, it's not the rate of change. Impulse is the force times the time equals to the change in momentum. That's a useful thing to recognize. Let's see how we can use this. When a golfer strikes a ball, it is in contact with the club head for about 1 millisecond, and the ball leaves the club head with a speed of 70 meters per second. If the mass of the ball is 50 grams, estimate the maximum accelerating force exerted on the golf ball, stating any assumptions you made. So that's the problem. We put these things together and we're going to use impulse to help us. If we think about the answer now, so try and calculate that before I try and go through and explain the steps. We know that force times the amount of time taken is equal to the change in momentum. Okay. We know that the change in momentum is going to be equal to mass times the change in velocity. Therefore, I can rearrange this and I can recognize some key things here. Okay. Number one, the change in velocity is going to be equal to 70 meters per second, because the ball was initially stationary, so 0 minus 70 minus 0 equals 70 still. The mass is given to us by the ball, so that's 0.05 kilograms, and the time taken, we have the contact time provided, which is 0.001. That means that my answer equals 3,500 newtons. Now I have made some assumptions here. I've assumed that the force applied to the golf ball is constant during that contact period of time. Okay, so I'm assuming that it's the same value all the way through. That's that key assumption there. In reality, what's likely to happen is there's likely to be a change in force over that period of time. Now, we can do calculations for this as well. For instance, with a changing force with time, as long as we have a graphical description of that, then we can work out what the impulse is and the change in momentum by looking at the area underneath the graph. So the area underneath the graph is equal to the impulse, and therefore we can use this to help calculate the speed at which the football leaves the foot for this question. We recognise the impulse is equal to 9 Newton seconds. 9 Newton seconds is equal to the mass times change in velocity. So therefore, if I divide 9 by 0.4, it gives me the velocity of the ball is going to be 22.5 meters per second. And that is my session on impulse. I hope it's been useful.